So we're still in part 3 and we just saw our results on the Ramusi 2 model. And now we're going to show you how FWIME can successfully invert a dataset dominated by diving waves on the North Sea region of the BP 2004 model. As for the previous example, we begin by a brief description of the experiment setup, and then we summarize the main challenges associated with this example. Indeed, we show that conventional data space multiscale FWI fails to retrieve a useful solution. And finally, we show that our FWIME workflow is able to retrieve an excellent solution. And furthermore, we are going to closely examine the different components of our cost function, and we're going to show that their behavior is also in agreement with our theory. This panel shows the region we selected from the BP 2004 benchmark model, which is referred to the authors as the North Sea or the Caspian Sea region. We selected this model to assess the ability of FWIME in inverting a dataset dominated by diving waves without the use of reflected event. The section is approximately 28 km wide and 5.5 km deep. We generate a noise-free synthetic dataset with a surface acquisition where we set sources every 160 meters and receivers every 40 meters. We record the data for 12 seconds, and the maximum offset recorded is approximately 27 kilometers. We use a source containing energy restricted to the 3 to 9 frequency range, and finally our modeling is conducted with an acoustic isotropic engine, which is also used for the inversion process. The first main challenge is the lack of low frequency energy in our seismic source, whose spectrum in decibel is displayed on this plot. The second challenge is that our initial model is extremely inaccurate, and its velocity value increases linearly with depth. This panel shows the initial velocity model used for both conventional FWI and FWIME. You can clearly see by examining these depth velocity profiles extracted at 19, 21, 22, and 22.5 kilometers that the initial model is extremely inaccurate, and in some regions of the model, the velocity error reaches almost 2 kilometers per second. This is also confirmed by looking at horizontal velocity profiles. And moreover, we can see that the true model shown in the red curve also contains high wave number features that are indeed absent from the initial model, as shown in the blue arrows. This numerical test assesses our algorithm's resilience to overcoming the cycle skipping issue, as the initial guess is missing both the long and short wavelength features present in the true model. The first difficulty resides in first recovering the low wave number components shown in the region within the box on the right panel. The second difficulty is to then recover the high wave number features present in the true model. They include the low velocity anomalies in the shallow part and the high velocity anomalies right underneath the mud volcano. The third challenge stems from the fact that our dataset is mostly composed of diving waves with very little reflected energy, which we know is very useful for our method to update the low wave number content in the model from the start. Moreover, as you can imagine, these diving waves are initially completely cycle skipped. These panels show two representative shot gatherers for sources placed at 0 km and 14 km respectively, and they're mostly dominated by refracted energy. So now that we have finished describing our experiment setup and defined our main challenges, we will conduct conventional data space multiscale FWI and show you that it has no chance of converging to an accurate solution. We conduct conventional data space multiscale FWI using 3 frequency bands spanning the 3 to 9 Hz range. We do not conduct any offset continuation, and we begin with the same initial velocity model described in the previous slide. As expected, the lack of low frequency energy combined with the inaccuracy of the initial model leads FWI to converge to a non-useful local minimum as shown in this panel. Note, however, that FWI is still able to correctly recover some of the low velocity anomalies in the shallow part of the model due to the available long offset recordings. And to better compare our FWI results, this panel shows the true velocity model. And let me flip a couple of times between the two panels. Okay, so now we begin by describing our FWIME workflow. And we start with the parameter selection. So the same initial model is used for the FWIME inversion. The full data bandwidth is simultaneously inverted and all the events present in the recorded data are injected from the start, again We did not select a separate reflections, refractions, and direct arrivals. For this example, the kinematic error in our predicted data stemming from the inaccuracy of our initial model, combined with the large offset recordings, were such that our time lag extension had to span a much wider time range than for the Marmousi 2 model. In fact, we used a time lag extension ranging from negative 1.2 seconds to 1.2 seconds, sampled at 24 milliseconds. Our model space multiscale approach is performed with 4 spline grids. We assume no prior knowledge of the subsurface, and we use a sampling for the first grid of 2.4 kilometers in the x direction and 1 kilometer in the z direction. At each refinement step, we decrease the sampling in both directions by a factor of 2. And the fourth spline grid, which is the final grid, coincides with the finite difference grid. Our optimization is conducted with 220 iterations of LBFGS for the nonlinear part and 60 iterations of linear conjugate gradient for the variable projection steps. We applied no illumination compensation, and we used a gradient mask in the shallow region of the water layer. Okay, so now let's begin by examining the FWIME initial search direction and illustrate once again the benefit of our spline parameterization. The left panel shows the scaled initial FWIME search direction on the finite difference grid, and the right panel displays the ideal search direction, which is the difference between the true and the initial models. However, after mapping the search direction onto the first core spline grid, we can see that the low wave number signal that was initially present but overwhelmed by the high wave number component is now correctly recovered, and the FWIME search direction is improved. And now that we have obtained a promising search direction, we conduct our model space multiscale workflow. And similarly as for the Marmousi 2 example, I will now show the sequence of recovered FWIME velocity models after each spline grid. This is the inverted model on spline grid 1, and this was obtained after 80 nonlinear iterations of LBFGS. In fact, the inversion on this spline grid is the most critical step of our inversion scheme. At that point, the low wave number components of the true model have been recovered. This panel shows the inverted model after approximately 50 nonlinear iterations on the second spline grid, and the inversion seems to be going in the right direction. And though not shown here, we conducted conventional FWI using this inverted model as an initial guess, and we obtained an excellent solution, which is as accurate as our final FWIME model that we will show in 2 slides. And this shows the inverted model after approximately 30 nonlinear iterations on the third spline grid. And this is the final FWIME inverted model after 125 nonlinear iterations on the last spline grid, which coincides with the finite difference grid. And the recovered solution is excellent. Again, here we conducted this optimization problem until completion for the sake of this numerical example. For 3D field data applications, we would have probably stopped at the end of spline 1 or spline 2 and used the inverted model as an initial guess for FWI. I will now flip between this panel and the true velocity model in order to assess the quality of our result. And as you can see, all the low and high wave number features from the true model have been accurately recovered. This can also be observed by examining the same 4 velocity profiles that we showed at the beginning of the FWIME inversion process. The blue curve shows the inverted model and matches the true model almost perfectly. We observe the same inversion quality by looking at horizontal velocity profiles, and the results do suffer from slight edge effect, but they are due to the limited acquisition aperture. And the next step is to dissect our inversion process, but from a data space perspective. The left panel here shows the observed data for a shot located at a horizontal position of 0 kilometers. The middle panel is the predicted data computed with the current velocity model estimate, shown in the panel located in the top right part of the screen. Here, the velocity model is the initial model, and finally the right panel is the difference between the observed and predicted data. And each panel is displayed with the same grayscale. And now we're going to show you a sequence of 4 slides corresponding to the predicted data and data difference computed with the different FWIME velocity models obtained after each spline grid. This is after spline grid 1, after spline grid 2, and this is for spline grid 3, and we can already see a pretty good match between the observed and predicted data, especially at large offsets, and the difference begins to vanish. And finally, at the last step, the difference has completely vanished and our predicted matches perfectly the observed data. And the last component we're going to examine is the optimal extended perturbation, p tilde opt. In a similar fashion as for the Marmousi-2 example, we're going to look at both the zero time-lag cross-section of p tilde optimal as well as a common image gather extracted at a horizontal position of x equals 22 kilometers. And we're going to show you a sequence of 4 different slides corresponding to the optimal extended perturbation computed after the inversion on each spline grid. And the velocity models used to compute p tilde optimal are displayed in the top right panel of the slide. Again here, observe how the energy is spread away from the physical axis on the common image gather on the right panel. In fact, some energy is even located close to negative 0.1 second lag. You will see that as the inverted model becomes increasingly accurate, the energy will first focus towards the physical axis and eventually vanish. And this is after spline 1, and this is for spline grid 2, and you can already see from the common image gather that the energy is well focused in the vicinity of the physical axis. And this is spline grid 3, and this is for the last FWIME inverted model. And you can see that most of the energy in p tilde opt has completely vanished. Again, we really hope you enjoyed this numerical test, which was the latest result we obtained in April. What we liked about both the Marmousi-2 and this example is that we successfully inverted different wave types with the exact same algorithm, without the need to select any specific components from the events in the data. Everything was simultaneously inverted and we obtained excellent results. In both cases, we used very inaccurate initial models and we did not have access to low frequency energy. And in the next video, we will show you a numerical example kindly proposed to us by Jean Virieux, former head of the SciScope Consortium in Grenoble, during his visit last year at SCP.